Thank you.
Yeah, maybe just a few more words on Fraunhofer CML. You've heard a lot of Fraunhofers today. We're sitting in Hamburg, so that makes a connection to the maritime domain. And what we do is like innovating the maritime domain. You can imagine the whole maritime supply chain has a lot of complex problems to solve. Routing a lot of ships in a fleet where you have like 500 ships and you want to plan them, it's challenging. If you want to stack in a smart way 24,000 containers on on the ship or 10 times on a port like Hamburg, and if you want to route them in the hinterland, then you can imagine that there are a lot of challenges that end up in mathematics into those cold and hard problems that we try to tackle at Fraunhofer. But maybe I'm not the right person to give such insights into what's going on in shipping, so I will hand over to Nils to give you some more insights.
Thank you. Harren Group is a Germany-based, Bremen and Hamburg headquartered shipping company. We own ships, we manage ships, and we operate ships. It's around 70 owned ships overall that we operate, and that's a global business in different cargo types. So we are actually probably quite far away, really, from quantum in the first place. We definitely represent the real world problems, and we have a lot of them. If we look at what we do, it starts from financing via procurement, via actually operating the ships in different areas. And then we had quite a number of conversations on how can we, or where do we potentially have areas where we could start to trial into quantum computing as a solution or as a means for finding solutions and optimizations. And we looked into routing. So we have a number of ships, for example, trading in the area of South America, and they are on a sort of liner service from Houston all the way to different ports in South and Central America, back to Houston area. And then we looked at what are the influencing factors to find an optimal solution. And first of all, what is an optimal solution? First of all, that's of course happy clients, but we put that aside because that's not so easy and precisely measurable. But when we looked at the cost, and the cost primarily is around the fuel, and the fuel has a second implication because the fuel more or less directly represents the CO2 emissions. CO2 emissions become a cost factor as well, but at the same time, of course, we have a clear aim to reduce that overall, not only because of regulatory requirements asking us to do that, because that's increasing on an annual basis, but actually also from our own company culture, we aim to reduce it. So that's kind of where we focus on optimize those routings. Now, if we look at what are the influencing factors on finding the optimal pathway through the sea, then you see on this slide a number of different factors that do influence that. And we just thought that this is by far too much. So we tried to select a few that are of impact and that are kind of measurable in order to build a model around them. And those are the marked ones, those in orange. So first of all, we have a load pod, we have a discharge port. That's obvious. And then we took into consideration the cost, which is primarily the bunker, and the CO2 cost, which is directly correlated. So if we go to the next slide. Yeah. Don't know if you see it, but we see it. So the input data is, of course, the starting point and the end point of the voyage. The second one is the transportation costs, now primarily represented by the bunker cost. Bunker is from, just for those that are not familiar with shipping, bunker means fuel cost. So that's just the shipping term for fuel. And the CO2 emissions and the CO2 cost. The constraints is primarily the time frame in ports and the requirements we get from customers, and the technical route constraints are, of course, the specification of the voyage orders. Then we have as a goal of what we're looking for as an output is, of course, to see what's the right sequence of ports. Do we find specific routes that are kind of optimal in this kind of frame that we set? And is there a potential to save not only cost but especially also CO2? Now, the baseline where we're starting from is actually we think we do it quite well already. But the way we do it is more manual in a way, because it's done by based on a lot of experience by a lot of people that do it every day. They talk to clients, they talk to the ships, they talk to the weather forecasting companies, and they try to do the best. But it's kind of manual, really. And this is where we started our conversation to see, okay, how can we get better from this starting point, which is sort of manual, not really manual, but there's a lot of room, I guess, where we can improve.
Yeah, and you already mentioned that we already limited the problem and the problem definition. Otherwise, we won't get done with all these different factors. Once for the classical, and then we move on to quantum, then we have to further limit it. And that's what I'm going to talk, what we did some very first step. So we do all those kind of optimization stuff in classical meanings. We write their heuristics. We have a lot of domain knowledge and can solve big, quite large data instances. Today we're talking about how to decompose them further and put that into a quantum computer or a quantum annealer or whatever we have nowadays. So what we did a decomposition, not in the mathematical sense of decomposition, a domain-driven one. We said we just solve shortest path problems, and we define at the very beginning, set the velocity as a very constant input parameter. So for each velocity that we know the fuel consumption, the CO2 costs, we run a shortest path problem. In best case, we run like millions of such shortest path problems and do post-processing. That's the way we included the domain knowledge. It's a way to go. So we do the decomposition, reduce the complexity, but still leave the problem into a realistic framework. The modeling approach, as I mentioned, shortest path, we transformed it into Cubo, maybe a little bit more technicality behind. Classically, you know that's this edge-to-edge distance matrix that you try to go through in the shortest path problem without any special constraints. We transformed it into Cubo when we put like vertex-to-vertex connections, and the penalty terms, you find them in the off diagonal. So what do I mean by that? We try to penalty if the ship goes from node 1 to 2, then it has a higher penalty if it tries for the same timestamp to go from 1 to 3. So to avoid this kind of movement. We modeled that as an undirected graph to save variables, to keep it small. And the current instance size that we have been looking into was the six ports, which is one of the realistic routes that we saw on the slide before. It's not like very theoretical, but it's not the best instance that you have every day. In Kubo, it means we have a Kubo size of 15 out of this with the 6 ports and the distance matrix. So we can use the pure quantum annealer of D-Wave instead of the hybrid one. We had some other projects going on with a hybrid annealer, and then we heard also yesterday, I think, and today in the morning, in the hybrid annealer, you don't really know what part of the problem is solved in some high performance cluster and what part of it is really quantum. So if you want to find something out, how much quantum can speed up, then we try to really reduce that Kubo and fit it into this pure quantum part. And it ended up calculating those kind of instances in 1 or 2 seconds, and 90% of the time is communication. So it's the solution is in milliseconds. So it has potential for the case that I previously mentioned. If you really variate your velocity and want to calculate millions of shortest paths, then it could work. Largest instance that we could calculate is 12 ports. Otherwise, we have to move on to the hybrid solver. It doesn't really make sense to compare the stuff with quantum. You see our logic nodes graph, logic qubits, how their connection, the 15 size of the graph of 15 nodes, and the smaller instance, we have seen it two presentations earlier that D-Wave has this kind of topology, and this is what's going on in D-Wave on the hardware side, the real qubits, the physical ones, and this is the representation on the logical level. Well, were very, as I said, with very first results with a very small instance where we put our main efforts to define it to still remain realistic. But what we are planning and aiming as next is to go through this kind of steps that you anyhow do in the classical way. So you have your real world problem, you formalize it, you lose some of the reality when you formalize, then you go and try to decompose, either by means of mathematical models or by domain knowledge or by combining them together. In case of quantum, we see, yeah, we need QUBO, but at some point in time, we maybe won't need QUBO. There would be some methods that brings you from the mixed integer linear program directly to the solving part. We have to check. You tune your solver, whatever solver you have. Sometimes also classical solvers need to get tuned. And take a look at the solution and do the whole loop again to get the best, to get as realistic as possible. And nowadays, everybody, I think, mentioned it, gate-based machines are too small, far too small for such problems, but we still have to keep an eye on them and try to find out what are the steps that we need to change to model, to change in our modeling, to put all the stuff into the gate-based machine. And a lot of time goes in the interplay between quantum and classical computations, so maybe we should put some more efforts in enhancing the formulation, which maybe can also help for the classical side. We know all this kind of NP-hard problems are formulation sensitive. We heard it in the previous talk too. What are the next steps? There are some potentials. There is quite a new publication that shows that for large scaling QAOA, for some problems, QAOA scales better. The best known classical heuristics, I have to check that. I don't know if it's really like that. We can put some more efforts to profit from this HPC quantum connection that is going on nowadays. Maybe we can take a look into using Grover for the processing, for searching. The best, if I'm going to calculate millions and trillions of different shortest paths, then I have another problem of searching in this space that will become very big if I keep the velocity continuous. So maybe we can check how to use Grover for that, and make maybe a deeper analysis on the interplay between models and solution methods. How do they impact each other? Are there something that we can change in the way that we model the problem in order to best fit currently existing methods? So move on from just trying to speed up and see how can we bring this both worlds together, like the real world and modeling with the solution that where we in both these ways we have some ongoing developments. So as I said, why quantum computing, we want to focus on the methods but not lose our focus from the real world that needs solutions. We want to gain some know-how and experience to check out on the right time pitfalls and tricks. And finally, of course, to test the potentials of quantum computing to speed up those kind of problems. But this is our roadmap from the technical side. But there is also another view from the reality that Nils would like to bring in, I think.
Yeah, I would actually just like to add. You could ask. I mean, and I'm getting asked, why are we doing this, right? I mean, obviously, I mean the room isn't full. Maybe we are very early in this process. I mean, actually we are. Do we get a proper solution really to our questions right now? No, not yet. I mentioned about our company size, so we're a medium-sized company. We have to adapt like every day to changing requirements. We have to be pretty agile all the time in all the aspects that we do. And that's actually our company culture, to be really open to explore what is there and what could potentially be out there as solutions that we don't even know yet. And this is probably one of them. Well, it's not that there to really be used. And we are getting a picture from those questions that, first of all, the questions that we actually boiled it down to was quite far away from our actual overall question. So the picture, even the result we got from that, was still kind of blurry overall, right? So it's not there yet, and we are aware, and this is not a problem. For us, it's much more about kind of trying, exploring, and testing and trialing what could be out there for solutions. And the way we usually do that is by not having specific departments or specific knowledge or kind of a lot of scientists on quantum computing in the company, because we simply can't do that. We can't afford to do that. So we always kind of team up and collaborate. And what we usually do in many different aspects, and this is again one of them, we either offer a problem or we offer a ship as an environment for a trial for startups to simply test out their solutions if we find them interesting enough to actually run those tests on one of the ships. So we are very aware that where we are today, this is not yet where we kind of need to be in the end, but we find it really interesting and see the potential, and this is why we are in it. So we are really looking forward to this collaboration to see how can we either formulate the problem in such a specific way that we get results that do help in our real life every day, or do we just need to be a little bit more patient, do some kind of trials, research, etc., to see at what stage can we have the problem like large enough, computed well enough to come to a solution that is applicable really in our daily lives. So our approach is simply to give it a try early on in order to be able to leverage on it whenever it's really there. So for us, this is a very interesting journey, and I would actually like thank you very much for doing this with us. And I think with this, we have a little bit
at
time
the end of our presentation and have a little bit time
for
questions and discussions. Thank you.
Okay.